Welcome back to the deep dive. You know, the pace of AI development, it just keeps accelerating, doesn't it? And it makes you wonder, how far can this tech really push the boundaries of what we know?
Right.
Could AI actually be the key to unlocking, scientific breakthroughs we can barely imagine right now? It's sort of the long-standing dream.
It is. And that's precisely the core challenge, isn't it? For AI to genuinely drive discovery, it needs more than just processing power. It needs a deep, a really nuanced understanding of human knowledge, especially knowledge right at the cutting edge.
Okay.
And that leads us to something called Humanity's Last Exam, or HLE. It's an exceptionally tough benchmark designed for exactly this.
Humanity's Last Exam. That sounds pretty intense. What exactly makes HLE so challenging for an AI, and why is doing well on it such a good sign for, real scientific research capability?
Well, it's intense because it wasn't just thrown together. It involved a huge global collaboration. We're talking nearly 1,000 subject experts, over 500 institutions. Yeah. And it's not just like a standard test. It's full of diverse, really expert-level challenges, problems right at the frontier. So if an AI agent does well on HLE, that's a strong indicator, a really good sign that it can handle complex, open-ended scientific problems, like a human expert might.
That definitely sets a high bar. So our mission today for this deep dive is to unpack how this new AI system, SciMaster, didn't just take this massive exam, but actually set a new, pretty remarkable standard. It beat the previous leaders, and it gives us some valuable clues about how AI can approach science. So, okay, let's unpack this. How did they pull off such a big leap?
It really comes down to a two-part strategy, and it starts with the foundation, the core architecture, which they call SciMaster, singular.
SciMaster, singular. Okay, the building block. What's special about that foundation?
So SciMaster is what they call a general tool-augmented reasoning agent. The thinking behind it is actually quite clever. It's designed to mimic how human researchers really work.
How so?
Well, it doesn't just rely on its internal knowledge, its training data. It actively, flexibly interacts with external tools while it's reasoning. So it's out there seeking information, using specialized functions, just like a person would. It's not just recalling facts. It's more like it's designing its own solutions on the fly, like an engineer tackling a new problem. It gives it this adaptable autonomy.
That sounds like a pretty fundamental shift in how AI tackles problems. You mentioned code as an interaction language. Is that the key mechanism here? How does that work, and what are the benefits?
Absolutely. That's central. When SciMaster hits a wall, something it can't solve internally, it doesn't just, guess or give up. It formulates a specific plan as a block of code. Python code, usually.
Okay.
Then that code gets executed. It can interface with powerful libraries like NumPy and SciPy, the heavy-duty math and science toolkits, or even custom-built tools. And the results, they get fed right back into its reasoning process, seamlessly. And this has three big advantages. First, universality. You can implement almost any function with code. Second, accuracy. Code demands logic. It's compact, less ambiguous. And third, compatibility. It gets instant access to the vast ecosystem of existing Python libraries. It's like the AI telling itself, okay, time to use the right tool for the job, instead of just thinking harder.
That's really neat. But, okay, here's a question. How do you make a model behave like that, like an agent using tools, without having to go through massive, maybe really expensive, specialized training?
Yeah, good question. That's where they use this clever technique called initial reasoning guidance.
Initial reasoning guidance.
Exactly. What they do is they embed these guiding texts written from the agent's own perspective right into its context when it starts working.
Like prompt engineering, but more embedded.
Sort of, yeah. Think of statements like, I can answer this query effectively by leveraging access to external environments, or every time I determine the need for interaction, I will generate Python code. It effectively primes the model to sort of believe it has these capabilities. So it just starts generating and executing code spontaneously without needing specific fine-tuning for that behavior.
So it bypasses a lot of the heavy lifting of traditional training for new skills.
Precisely. It's a way to unlock this advanced agency in these powerful models with surprisingly minimal intervention. Makes it much more accessible.
So it's kind of priming the AI's mindset. And part of that human-like approach is actively seeking info, right? What tools does SciMaster have for that information gathering?
Exactly. It has custom tools. First up is a web search tool. It uses Google, but it's smarter than just a basic search.
How so?
It pulls out key facts about entities it recognizes, gives you previews of relevant pages, title, URL, snippet, and even suggests related searches, like a really fast research assistant anticipating your next move.
Okay, so it finds potentially useful pages. Then what? How does it actually use that information?
That's where the second tool, the web parse tool, comes in. This is for digging into those results.
Yeah.
It actually has two modes.
Two modes.
Yeah. For a general web page, it tries to extract the main content, figure out which parts are most relevant, and even find links to subimages so the agent can explore further if needed.
Okay, makes sense. And the second mode?
That's specifically for scientific papers. It tries to grab an HTML version first from R5.
Yeah.
The preprint archive.
Right, ArcSys.
Oh yeah, ArcSys, sorry. If that doesn't work, it falls back to downloading the PDF. Then either way, it extracts the bits of information most relevant to the original query.
So it's not just finding pages, it's actually encouraging this process of searching, scanning, clicking links, digging deeper, really mimicking how a person researches online.
Exactly. It promotes that kind of exploration.
That sounds incredibly powerful for just one agent. But you said this system is called SciMasters, plural. Does that mean they work together?
Absolutely. The individual SciMaster with its tools is already very capable. But the researchers thought, okay, for the really hard frontier science problems, even a brilliant individual often needs a team, right?
Sure. Different perspectives, checks and balances.
Precisely. And that's what SciMasters plural provides. It's this multi-agent workflow they designed. They call it the scattered and stacked agentic workflow. It's built to scale up SciMaster's intelligence at inference time, when it's actually solving the problem.
Scattered and stacked. Okay, that sounds interesting. Like a core part of the system. Can you walk us through that? How does a problem actually move through these stages? What's each agent doing?
Yeah, think of it like a well-coordinated research team tackling a complex challenge. There are 4 main stages, each performed by instances of SciMaster taking on specific roles.
Okay, stage 1.
Stage 1 is the solver. These are like the initial brainstormers. You get 5 of them working in parallel, each generating an initial solution using that tool-augmented reasoning we talked about.
5 different starting points. Okay, then what?
Then comes the critic stage. Again, 5 critics working in parallel, 1 for each initial solution. They act like peer reviewers.
Ah, okay.
They evaluate the solution they're assigned, identify flaws, suggest corrections, basically poke holes in it.
Critical feedback. Makes sense. What's next?
Next is the rewriter. This one acts like a synthesis expert. It gets all the previous outputs, the 5 initial solutions, and the 5 critiques.
All 10 pieces of information.
All 10. And its job is to synthesize all of that to generate 5 new, hopefully superior, refined solutions, again, in parallel.
So it's integrating the initial ideas with the critiques. And the final stage.
The final stage is the selector. This is like the lead investigator or the final judge. It looks at the 5 rewritten solutions and picks the single best one as the final answer.
Wow, that's a very structured process. Solver, critic, rewriter, selector. What's the underlying idea behind this scattered and stacked name? Why that structure?
It's actually a really neat analogy they draw to something called rollouts in reinforcement learning.
Rollouts, like exploring possibilities.
Exactly. Think of a chess AI exploring many possible sequences of moves. The scattering phase, the solver and critic stages working in parallel, is like that exploration. Each agent explores a different reasoning path, which ensures you get diverse ideas and don't just latch on to the first plausible answer.
So that's the breadth part. What about the stacking?
The stacking phase, primarily the rewriter and selector, is like the aggregation step. It's where you take the insights from all those parallel explorations and combine them, exploit them, to build a single, much stronger, more refined solution.
Ah, I see. Scattering for breadth, stacking for depth and refinement.
Precisely. It creates this balance between exploring widely and then really drilling down to get the best possible answer.
That really clarifies the workflow. So the big question, with this whole sophisticated setup, how did SciMasters actually do on humanity's last exam? What were the results?
The results were, frankly, remarkable. SciMasters achieved a score of 32.1% on HLE.
32.1%. Okay, how does that compare? Is that good?
Right.
What were the previous benchmarks?
It's not just good, it's a significant jump. It surpasses OpenAI's Deep Research System, which got 26.6%, and Google DeepMind System, which was at 26.9%.
So beat them by, what, 5.5 and 5.2 percentage points? That seems like a solid lead.
It is. And importantly, it's the first time any system has broken the 30% barrier on HLE.
Ah, okay, so that 30% mark is kind of a milestone.
It really is. It's seen as a sign that AI is starting to grapple with knowledge synthesis at a level closer to human experts. especially for these tricky, open-ended science problems. It's a real testament to both the tool-using SciMaster agent and that whole agentic workflow.
And was this success concentrated in one area, or did it improve across the board?
That's another key point. It showed notable improvement across all the different categories within HLE compared to the baseline model they started with, which was already a strong model called DeepSeek.
So broad applicability, any specific examples jump out?
Yeah, definitely. In the biology and medicine category, for instance, SciMaster's got 27.6%. That beat specialized systems like Biomni, which scored around 17%, and Stella, which was around 26%.
Better than systems specifically designed for biomedicine.
In this benchmark, yes.
Yeah.
And on another test, PRQA-Lit, that's text-rich question, answering for biological research, the single SciMaster agent got 62.1%, but the full SciMaster's workflow hit 67.4% state-of-the-art.
Wow.
And what's really striking, they achieved this with just those two web tools we talked about, search and parse. They outperformed systems like Origin, which apparently uses over 500 expert tools.
Only 2 tools versus 500. That suggests the workflow itself is incredibly powerful and efficient.
Exactly. It speaks volumes about the power of the reasoning and the collaborative structure, not just having lots of tools.
Okay, to really understand why it's so effective, I know researchers often do these ablation studies. Can you explain what that is and what it showed here? It's like taking bits away to see what happens, right?
That's a perfect way to put it. You systematically disable parts of the system to see how much each part contributes. And the results here showed really clear progressive gains at each stage of the SciMaster's workflow.
Okay, walk us through it. What did adding each stage do?
All right, so just adding the tool-augmented reasoning, essentially the solver stage alone lifted the baseline accuracy by about 3.4 points up to 21.1%.
Okay, a decent bump just from using tools. Then the critic.
Adding the iterative refinement for the critic stage added another 3.9 points, bringing the score up to 25.0%.
So feedback helps. What about the rewriter?
The rewriter stage, where it synthesizes everything, that gave a really significant jump, another 5.6 points, pushing the score to 30.6%.
Wow, that synthesis step is critical.
Seems to be. And then the final selector stage nudged it up that last bit to the final score of 32.1%.
And you mentioned the rewriter seemed particularly important. How did the data back that up?
Yeah, if you look at their analysis, specifically figure 7 on the frequency of correct answers, it really highlights the rewriter's impact. Before rewriting, maybe only 1 or 2 of the initial 5 solutions might be correct. But after the rewriter does its synthesis work, the chances of all 5 rewritten solutions being correct goes way up. It essentially transforms those scattered, mixed-quality initial guesses into a much more refined, high-value pool for the selector to choose from. It really improves the overall quality dramatically.
It's like the team rigorously refining their best ideas before the final presentation.
Exactly like that.
So it really sounds like you need both parts of that workflow, the scattering and the stacking. The ablation study confirmed that too. You couldn't just do one or the other.
Absolutely confirmed it. The study showed if you remove the parallel exploration, no scattering, the accuracy drops right back down to 25.5%.
Okay.
And if you remove the depth-wise improvement, no stacking, no rewriting or selecting, effectively it drops to 25.0%.
So roughly the score you get after just the critic stage.
Pretty much. It's the synergy between them, the combination of exploring broadly and then refining deeply, that gets you to that top 32.1% score. You absolutely need both working together.
You know, what's also quite striking about this research, beyond the impressive results, is their approach to sharing it. It feels like they're not just presenting a novel method, but actively sharing the know-how.
I agree. That's a really important aspect. They explicitly demonstrate that you can achieve leading performance on these very difficult benchmarks using accessible open source models as the base.
Right. They didn't need some giant proprietary billion-parameter model trained from scratch just for this.
Exactly. They bypass the need for massive custom model training. And that really helps to democratize access to these cutting-edge AI capabilities, especially for scientific discovery. It encourages the wider community to participate and build on it, which accelerates progress for everyone.
It sends a message that top-tier AI research isn't only for the huge industry labs with unlimited resources.
Precisely. That's a very powerful message for the research community.
So wrapping this up, this deep dive really highlights a significant step forward, wouldn't you say? AI tackling complex science, not just with brute force, but by mimicking human research processes, using tools, collaborating through these structured workflows.
Definitely. It shows a path forward that's more about intelligent process design than just raw computational power, although that helps too, of course.
It makes you really stop and think about how fast this field is moving and how AI might genuinely reshape scientific discovery.
And that core message about open source power is key. Democratizing access, fostering community participation. That's how you supercharge innovation in science, showing these top benchmarks aren't out of reach.
It makes you wonder what comes next. Imagine these integrated, self-improving AI agents focusing on specific scientific domains. The paper mentions their SciMaster series aims to build on this, right? Developing specialized agents for literature analysis, scientific computing, experiments, maybe even end-to-end trained agents eventually.
Yeah, that's the roadmap they laid out, expanding the toolkit, specializing the agents.
So, thinking about that future, what new scientific frontiers do you think might be the first to see really transformative breakthroughs from this kind of AI-driven approach? Where does this kind of structured tool using AI make the biggest difference first?